indices to get expressions, terms in functions in a form that we can differentiate them when we come to that. So, and at that point we use these laws of indices quite extensively. We can also use them to help us simplify expressions. So we need to know what they are, make a note of them, perhaps have them on a piece of paper at the front of our file so we can refer to them regularly when we need them, and then eventually know them. So you might want to write down these laws on a separate piece of paper so you can put it at the front or something. It's up to you anyway. So the laws of indices. Well, first of all, that's what it's to do with. It's to do with a number, x, called the base number, raised to a power, a. So this is the power, or the index, hence the law of indices. So, for example, 3 to the power 4 would be base 3 power 4. And that, of course, means 3 times 3 times 3 times 3. We know that, I hope. Okay? So if I raise things to a power, it just means I'm multiplying it by that. It's by itself 4 times in this particular example. However, if I have this situation, x raised to the power a multiplied by the same base raised to the power b, for example, 3 to the power 4 multiplied by 3 to the power 2, then I think you can see that actually I'm multiplying 3 by itself 4 times and then multiplying it by itself another 2 times, so I end up multiplying it by itself 6 times. And so the law of indices, and this is the first law of indices, is that so long as the base is the same, and that's the key, so x, then I can just add the powers, and I end up with x raised to the power a plus b. First law of indices. Yeah, that's right. Yeah, so using that example, I could write equals 3 to the power 6. Yeah. No, the times 10 to the 6 is another use of indices, which is the standard form and engineering notation. So that's not to do with this, although it's related. Following a similar argument, if I were to divide a number raised to a power a divided by the same number raised to the power b, for example, 3 to the power 4 divided by 3 to the power 3, then hopefully you can see that that would actually equal 3 lots of 4, 3 times 3 times 3 times 3, sorry, 4 lots of 3, divided by 3 times 3 times 3, and then I could actually cancel, because 3's goes into 3 once at the top and the bottom, 3's goes into 3 once, 3's goes into 3 once, top and bottom. So in other words, I could cancel out 3 of the 3's on the top and replace them with a 1, and 3 of the 3's on the bottom and replace them with a 1. So I end up just with 3 to the power 1 effectively. And 4 minus 3 gives it to me. So I can actually subtract the powers. Equals x to the a minus b. And that's commonly referred to as the second law of indices. Subtract the powers. Yeah, subtract the bottom power from the top power, or the top power minus the bottom power. Third law, if I've got something like x to the a raised to the power something else, b, so this is the third law. This actually, the other laws, I think there are 5 of them altogether we're going to look at. No, 6 altogether. It turns out that they all are derived from the first 2, really. So, for example, 3 to the power 4 squared. Well, if we think what 3 to the power 4 squared means, it means 3 to the power 4, 4 lots of 3, multiplied by another 4 lots of 3. So I actually end up with 8 lots of 3. So in other words, if I've got a number raised to a power, and then that's raised to yet another power, I just multiply the powers together. So this turns out to equal x to the a times b, or ab. Multiply the powers. So that's the third law of indices. Then things start to get a bit more interesting, and we end up with two laws that, as far as calculus is concerned, are the two main laws that we use. The first one, if I think of an example, say 3 to the power 3 divided by 3 to the power 5, using the idea of what this means, 3 to the power 3 divided by 3 to the power 5, I get 3 times 3 times 3 over 5 lots of 3. 4, 5. Cancelling. Can cancel one lot of 3's, another lot of 3's, and another lot of 3's. So I can replace them with 1. So on the top, I've got 1 times 1 times 1, which is 1, over 3 times 3, or 3 squared. Haven't I? That makes sense? Just using that second law of indices. If, just using the idea of putting the 3's on the top, 3's on the bottom, what that means. This means 1 over 3 squared. But if I use the second law of indices, what does that tell me to do with these powers in this first one here? What does it tell me to do with these two powers? Minus them. What's 3 take away 5? Minus 2. So in fact, we end up with 3 to the minus 2 equals 1 over 3 squared, which leads us to the next law. If we look at this, a negative power means 1 over. 1 over. A negative power means the inverse. Written in terms of the law of indices, I'd write this. 1 over x to the power a, any power a, equals x to the minus a. The negative power means the inverse. A negative power means the inverse. 1 over. And that's quite an important one, certainly when we come to calculus. We also have the law of indices to do with squaring and cubing and things like that. Right, it's a bit further down so it doesn't interfere with this example. Right, that symbol, square root of 9, multiplied by the square root of 9. What does that equal? 9, yes. The square root multiplied by itself gives the number inside the square root, because that's what the square root means. What is the square root of 9, by the way? So Square root of 9 is 3, so 3 multiplied by 3 gives 9, which confirms it. Okay? So the square root of a number, and if we think about this definition, the square root of a number is a number which, when I multiply it by itself, gives that number. So the square root of 4 is a number which, if I multiply it by itself, gives 4, 2. The square root of 9 is the number which, if I multiply it by itself, gives 9. That's what we mean by the square root of a number. So if I can apply that to the idea of indices, what I say to myself is, okay, so if I have a number, let's say the square root of x, well no, I better leave this as an example actually over here because that's not the law of indices. So the square root of x multiplied by the square root of x gives x, to generalize. What's the power of this x here, by the way? 1, right. So x raised to some power multiplied by x raised to the same power has got to equal 1. So what must this number be from the first law of indices? No, what does the first law of indices tell us? Add them. So what two numbers added together give 1? A half. Well done. A half. X to the half multiplied by x to the half gives 1. The square root of x times the square root of x gives x to the 1. So fractions are to do with roots. The square root, and there's no number by the square root, but it's implied as a 2, the square root is to the power of half. We could follow a similar argument to show that the cube root, which is a number if I multiply it by itself 3 times gives the number, would have to be a third plus a third plus a third gives 1. So we end up with a generalization that the nth root of x equals x to the 1 over m, the fraction. And in fact we can generalize it further and say x to the n over m equals, sorry, the mth root of x to the n is x to the n over m. That's probably the most difficult one to get your head round, okay, as to how it works. You may need to go away and just think about how that little argument over here works again. But at the end of the day, what you have to remember is, and this is the thing, so for example, let's put a number here, e.g. the cube root of x to the power 4, for example, would be x to the 4 over 3. So m and n stand for the numbers by the variable x. So x raised to the power m, and then the mth root, n and m. The cube root of x to the 4 would be x to the 4 over 3. So if we look at this, the 4 is the number that goes underneath, or the m rather, looking at the general one. The m is the one that goes underneath in the fraction, and the n is the one that goes on the top in the fraction. As simple as that. The root is the one that goes underneath, and the power of x is the one that goes on top. What is it, Brad? What is that again? The root goes in the fraction, at the bottom in the fraction for the power, and the power of x goes on top of the fraction. Root underneath. What goes under the ground? The root. So that's the way to remember it, okay? Roots underneath in the fraction. Think of the root as being under the ground, underneath in the fraction. It's important to see this rule, as again, if you've done some maths with me, you'll know, because as soon as you get into calculus, how do I differentiate something like this, you write it like that, and then you can differentiate it easily. It's one step. You just write down the answer. It's not difficult. What makes it difficult is this bit, isn't it? Okay? It's always the algebra that makes things difficult. So these are two very important laws of indices, 4 and 5. The last one, number 6, says that x to the power 0 is 1. And I'm not going to prove that. I'm going to leave that for you to prove as a little exercise. Okay? Prove this. Yes. Prove this. Think about the laws of indices you've got already. Why would x to the power 0 be 1? Okay, so I'm going to, if you want